Alright, welcome to this video, and today we will be talking about how to solve cubics, and we will see how to derive the solution for it because there is a formula, but it is quite long and quite hard to remember. But we will go ahead and start with it. But let's go through a little bit of history of it just to see how it was found. So during the 16th century, a mathematician by the name of Scipione del Ferro, he solved a depressed cubic in the form of x cubed plus px plus q, or is equal to q, which you would usually write it as x cubed plus px minus q, but he wrote it as this because they didn't accept the concept of negative numbers, or, well, they weren't accepted in mathematics at that time. So what he would do was just keep all coefficients positive, and he found a reliable way to solve these types of cubics by completing the cube, which is a similar approach to completing the square, but he completed a cube with the depressed cubic. And how he did it was by adding onto the cube and then solving for a quadratic, which then gave the solutions to the cubic. But it's not like completing the square where you have x plus b over 2a squared and then the solution b squared minus 4ac all over 4a squared. You wouldn't get this step in completing the cube. So that's the main difference about it, because you would have to solve a quadratic in order to get the solutions to the cubic, which is what he himself did and understood. And with that in mind, he solved the cubic by completing the cube and being able to properly solve any types of cubics that involve that specific type, such as the one we have on screen, and possibly also x cubed plus q is equal to px, which he did solve several, but he only told one to his student, Antonio Maria Fior, which was the first one I wrote down, which is x cubed plus px is equal to q. And he showed it to his student, Antonio Fior, who then went on to challenge a much more tougher mathematician by the name of Niccolo Fontana Tartaglia. That is, my handwriting's horrible, but it's fine. So he went on to challenge Tartaglia, and Tartaglia imposed several cubic problems that were in the form of x cubed plus px squared is equal to q, which Fior obviously didn't know how to solve, since he knew how to solve this specific type of cubic up here and not the one with the quadratic term. So he lost the duel because he was not able to solve these types of cubics, which have the x squared term and no linear term. And with that in mind, we do have several problems that Tartaglia received from Fior, which are, I'm just going to write a few down in case anyone's interested. Since the first one was x cubed plus x is equal to 6, or the way he would write it would be, find me a number that added to its cube makes 6, which is basically find me a number that added to its cube gives out 6. So that's one of the problems that were recovered from that time. We also have another one which was much more tougher, which is the second problem in the dual, which was 4x cubed plus 3x is equal to 40, which was basically a problem written in the description like as said, find me two numbers in double proportion, i.e. such that one number is twice the other, such that the square of the largest number multiplied by the smallest and added to the first numbers is 40, which translates to this equation down here. So with that in mind, we see that Tartaglia also discovered a method on how to solve depressed cubics of that form, and he also did the exact same thing Scipio the Pharaoh did. He completed the cube. And he did it in such a way that he would be able to solve a quadratic and then choose which of the solutions for the quadratic to use, either plus or minus, but they would be the same solution. And with that, he understood that he could solve any type of cubic which was in the press form x cubed plus px plus q or equal to q is equal to 0. He realized that with his method, he could win the duel, and he did end up winning the duel in under 2 hours. But that's enough of the history behind the cubics. Right now, we will be looking at the formula derivation for the cubic, and then go ahead and test a cubic with one solution and three solutions. So we will go ahead and depress the cubic with x is equal to y minus b over 3a, which was discovered or understood by another mathematician by the name of Girolamo Cardano, who wants the solution from Tartaglia, and Tartaglia gave it to him, but then Cardano found the solution to the whole general cubic by considering substituting a value by removing its vertical shift, which is b over 3a. So that is what Cardano did and found the solution to this cubic up here that we have on screen. So we will see how we get this into this cubic. So we will transform the cubic and look at it right now and see how it behaves. So let's just start with plugging x is equal to y minus b over 3a, where we get a times y minus b over 3a cubed. Let's do it separately so we don't lose track of anything. So we have a times y cubed minus minus b over a y squared plus b squared over 3a squared minus b cubed over 27a cubed. So we have that. We don't really need to multiply a since we'll do that later. Next step, after we're done simplifying the equation, over 3a squared is equal to b times y squared minus 2b over 3a plus b squared over 9a squared. Put out of the y here and up here as well. And now we can now just do the c term, y minus b over 3a, which gives us cy minus bc over 3a plus d, of course, since we need to add d to keep the equation as it originally is. And now we will multiply a, so we get a y cubed minus b y squared plus b squared over 3a minus b cubed over 27a squared plus by squared minus 2b squared over 3a y plus b cubed over 9a squared, and so on. Let's just continue to write all this, and we get plus d. So it seems like we're worse off now than where we had originally started, since we have so many variables and so many numbers. And you're probably wondering, how do we make all of this huge expression into the press cubic that is shown up here? How do we get all this to become this? That is a question. But as we see, the two y squared terms cancel out. Let me just mark that in red so that we can see clearly that they do get crossed out. And we will now group terms and factor out some terms. And by doing that, we will get that a y cubed plus, let's look at the c terms first. This has y as well. We have parentheses c plus b squared over 3a minus 2b squared over 3a y plus d minus, I should just do descending order, minus bc over 3a plus b cubed over 9a squared, which we would get positive plus 2b cubed over 27a squared. Now dividing by a, we get y cubed plus c over a plus b squared over 3a squared. That is a horrible 2. Minus 2. Well, let's just do that, subtracting these two first, which we get minus b squared over 3a squared y. And we also end up getting plus d over a minus bc over 3a squared plus 2b cubed divided by 27a cubed. And we could set these to y cubed plus py plus q. And we see that we managed to make this entire expression to the cubic up here. But instead of x, it is in terms of y. So with that out of the way now, we can see that we finally depressed our cubic. So we will go ahead and look at the values and substitute them later into the formula. But for now, I will just clear up the board and I'll be right back. So now what we will do is, let me just fix this 2 up here. Now we see that p is equal to this expression inside the parentheses and q is this expression inside of this other group of parentheses. So we don't need to group all this because we could do it separately for now. So what we will do now is see how to solve the cubic now since we have it in this exact form. And we could use the perfect cube formula, u plus v cubed is equal to q plus 3u squared of v plus 3uv squared plus v cubed. And we see that there is a factor inside of 3u and v, and we could also group up the terms u and v cubed. So with that, we could get this expression above, x cubed is equal to u cubed plus v cubed plus, we can factor this out to get 3uv times u plus v. Now we just move right into a left-hand side where we would actually end up getting u plus v cubed is, or minus 3uv times u plus v minus u cubed plus v cubed is equal to 0. And now we see that we could express u plus v in terms of y. So let's write that above as well. Y is equal to u plus v because we have 3uv, which is also equal to p for now. U plus v is equal to y, and u cubed plus v cubed is also equal to q. So with that, we can now see that by substituting or making a substitution where p is equal to negative 3uv and q is equal to negative u cubed plus v cubed, we could get the formula from this. And what we could do now is make a clever substitution. First, let's divide by 3 and cube the whole equation. Minus p over 3 cubed is equal to u cubed times v cubed. And we just have to multiply by v, so we get q v cubed is equal to, or negative q v cubed, we get u cubed v cubed plus v to the power of 6. So now, let's just substitute u plus v for u plus v cubed for p over 3, or minus p over 3. And our equation that we will end up getting is v to the power of 6 plus q v cubed plus negative p over 3 cubed is equal to 0, which is a quadratic in disguise in terms of v cubed, where we get qu plus negative p over 3 cubed is equal to 0. So we will just write it in terms of v cubed is equal to minus q plus or minus the square root of q squared minus or plus, since the minus cancel out, we get plus 4 times p over 3 cubed all over 2a, or 2 by itself. Now, just messing around with this, we could end up getting v is equal to the cube root of q over 2, or minus q over 2, plus or minus the square root of q squared, or q over 2 squared, since we're basically fitting 2 into the square root. It's going to be 4, which cancels out the 4 and the 4, so we end up getting q over 2, or q over 4, which we could write as q over 2 squared, because that's the same thing as q squared divided by 4. Now we also get plus p over 3 cubed, which is the formula for v, and also u, because if we were to do u now, we would get the same thing. So we have to find out which subset of solutions are true, because we have the pair of plus and plus, plus, minus, and minus, and minus. And only one of them is true. In this example, we know, or we see that the only true pair that would work is plus and minus. So we will go ahead and clear up the board and see how the whole cubic formula looks now by plugging in q and p. So I'll be right back just to clean this up. So now that we have more space now, we see that y is equal to the cube root of this expression, but one is plus and the other is negative. So in this example, we'll say that u has the plus inside the cube root, and the v has the minus sign in front of the square root. So we will now substitute q for its values, which is this expression in red, and we're going to substitute p in the blue. So with that, we will see how the long formula looks, and we will end up getting our solution to or for x. So we're just going to say x is equal to minus b. Actually, no, I'll write that at the end. We're going to make the long radical sign. That was weird. The cube root of all of this divided by 2, which we see that 2 b cubed divided by 27a cubed times 2, which is going to give us minus b cubed over 27a cubed plus bc c over 6a squared minus d over 2a plus or minus the square root of the whole expression but all squared minus b cubed over 27a cubed 6a squared minus d over 2a squared. Seems like we're going to expand this out a little bit. Plus p, which is c, where we get c over 3a minus b squared over 9a squared, all cubed. And we could get we could write the whole thing down, which I might as well just do that now. So we can see the sign b cubed over 27a cubed plus bc over 6a squared minus d over 2a minus everything I just wrote down, all squared, minus b cubed plus bc over d, and then we'll just do 2a, 6a squared, 27a cubed. Oh, why? There we go. Plus c over 3a minus b squared over 9a squared, all cubed, minus b over 3a. And let me just see if I could get rid of that minus, because that's gonna just confuse some people. There we go. So we have the long cubic formula, which is written like this, which this formula is quite hard to remember and quite long. And we see that it has two complex, well, it has quite the complex solutions as we see, because we have a long cube root and a square root, which is going to be quite time consuming if we actually were to solve it. So we get this long formula here, which is the solution to a general cubic in terms of A, B, C, and D. And we will now go ahead and look at some worked examples. But first, let's just clear this up really quick since we don't need most of this stuff here. Let me just clear this up really quick. And also as well this, and I will move this up. So we have our solution now, and we will look at some examples to see how our formula works and how it acts. Since it does have some strange behavior, but we will get to see how the formula works. So right now, what I will say is that when the discriminant is greater than 0, it has one real root and two complex roots. If the discriminant is equal to 0, then it has one real root and a repeated root and repeated and repeated root and a repeated root. So I got meant to say. And when the discriminant is less than 0, it has three real roots. So that's what's going to tell us what's inside of the square root. where we see that if we were to go ahead and try to make this negative, then that would give us three whole solutions. But we're not going to use the long formula, but I will for one example. So I will go ahead by starting off with a simple cubic to solve with the depressed cubic formula. So we get x cubed, that was a horrible 3, cubed plus, or no, minus 6x minus 9 is equal to 0. So let's use the formula for this. X is equal to the cube root of 9 over 2 because we have minus q over 2 right here, which is positive 9 because they're both negative, and a negative cancel each other out. And we're going to write plus or minus to now write the other cube root, where we get 81 over 4 minus 2/6 over 27, which simplifies down to the cube root of 9 over 2 plus or minus the square root of 81 over 4 minus 8. And now what we can do is multiply this by 4 and make it into a fraction. And if we do 81 minus 32, we get 49. So 9 over 2 plus or minus the square root of 49 over 4. We end up getting the cube root of 9 over 2 plus 7 over 2, which then would give us x is equal to the cube root of 9 plus 7, which is 16, divided by 2, which is 8, plus cube root of the minus sign now, which is 9 minus 7, which is 2, divided by 2, which is 1. And we get the cube root of 8 is 2, and the cube root of 1 is 1, and we get 3, which is a solution to our cubic. So let's just write that up here, keep track of what we've done. And what are the other two solutions? We should have 3 solutions in total. Well, what we can do now is use the roots of unity by multiplying this. Let's just do times -1 plus I root 3 over 2 plus 1 times -1 minus I root 3 over 2. And doing this, let's just do a little bit of simplifying. This becomes -3 plus I root 3 over 2. Since if we were to multiply all this by 2, we would get -2 plus 2i root 2i root 3 over 2 minus 1 minus I, which -2 minus 1 is -3. And 2 plus 1, or 2 minus 1 is 1. And we would get this. So we end up getting our first pair of the complex solutions we get. But we could get the other solution by just adding a minus over the plus, indicating that we have a conjugate pair, because every complex solution comes in its conjugate pair. Take the example x squared plus 1. The solutions are x is equal to the square root of -1 plus or minus, which is equal to x plus or minus I. So just remember that if you always have a complex solution, it always comes in a pair. Like this, we have 2 solutions from just doing a little simplifying with the roots of unity. So with that in mind, we could solve any cubic that we want with using the formula and as well as solving it with the roots of unity. Because you could write this exact formula all over again times the roots of unity for each cube root, but that would give you 3 cubic formulas, but you have to solve about 6 or 12 different radicals, which is including the square roots and the cube roots, since that would take a lot of time. So it's better to just do the first cube root, and then when you have the final result, just times it by -1 plus I root 3 over 2, and plus -1 minus I root 3 over 2 to get the other two pairs. And if you have the cubic formula with radicals, for example, like if you have a cubic formula like this, 1 over 9 plus the cube root of 5 over 9, you would basically have to multiply both by the negative sign, -1 plus I root 3 over 2, both for this one on the right side, and as well as -1 minus I root 3 over 2 to get the other ones, or the other solution, which would give us the cube root of 1 over 9 times -1 plus I root 3 over 2 plus the cube root of 5 over 9 times -1 minus I root 3 over 2. And just to find the other pair, just switch the sign of plus or minus in front of the I. But that will be for another topic. So with that out of the way, we found our three solutions to the cubic. X cubed minus 6x minus 9 is equal to 0. So let's just go ahead and clear all of this up. And I will solve one more cubic. So let's go ahead and solve one more depressed cubic is equal to 15x plus 4. Let's just move everything to the left-hand side just to set it equal to 0. And now let's just use the formula again. And we get x is equal to the cube root of 2 plus or minus the square root of 4 minus 3,375 over 27, which is equal to the cube root of 2 plus or minus 4 minus 125, which is equal to the cube root of 2 plus or minus 4 minus 125 is 121, and 11 or 121 is a perfect square, so we get plus or minus 11I, because the square root of 11 is 121, and we get that x is equal to the cube root of 2 plus 11I plus the cube root of 2 minus 11I. And what do we do now since we have complex roots now? Well, this indicates to us that we have three different solutions, all distinct, because this equation here looks something like this, since it has quite the long curve because of the 15 of or the negative 15x. We see that it has a slope of negative 15, which causes the cubic to stretch out negatively or have a slope of negative 15 in its inflection point, which then causes it to go down, then go up. And we can see how this almost resembles the original cubic like this, with the shape of its original form. And it's just stretched out like this, only negatively, because the center part is just stretched out by negative 15x, since it has a slope of negative 15. But enough of that. I will get into talking about polynomials in a future video. And here we have this long formula. Solve the next cubic we're about to solve. But first, let's go back to our original problem. Since we have x is equal to the cube root of 2 plus 11 I root, or I plus the cube root of 2 minus 11I, we solve it using either a system of equations, or we could solve it by Demar's theorem, which would be quite time consuming because you're using the polar form of complex numbers and understanding their place in the complex plane, and also using a little bit of trigonometry to pinpoint the solutions. But if we were to guess and check and look for rational solutions, we would find that x is equal to 4. That is one of the solutions that we would get. And by factoring that out, we would get the other two solutions. But why does our solution not equal 4? Why does it not equal 4? Well, the reason is it does equal 4 in reality, but it takes a little bit more simplifying to get to the solution of 4 and the other two solutions, which are -2 plus root 3, if I'm not mistaken. But those should be the solutions for the cubic. And if we look at this, we don't see any of this from this expression at all at first, but we could see that we have the 2's in common since we have our cubic is divisible by, we have the first whole number 2 both in our solution, which is 2 squared and -2, but we don't have the square root of 3, which is what we're mainly wondering why we don't get that from our formula. And the reason is because we need to accurately solve using the Marv's theorem or solving it with the systems of equations that we earlier had to discuss about. So we end up with the solutions of a cubic equaling this, which is, how do we solve these exactly? We could use the Marv's theorem, but for now we will just say x is equal to 4 and -2 plus root 3, because I will get into a video on this soon and how to solve this using the system of equations and the Marv's theorem on the same video. But just know that cube, this complex cube root gives out 4 and -2 plus the square root of 3. So we could write those are our solutions here. -2 plus root 3. But if you want to watch the video on Demar's theorem and solving systems of equations or using systems of equations to solve complex numbers, then I'll make a video on that soon. So just be in mind and be aware of that. So that's that for this cubic. We will now go ahead and look at a whole general cubic with, well, we're going to look at an easy example so we could get the main idea of the cubic formula, which we're going to look at this, or not 3, -1 cubed, which is the same thing as x cubed minus 3x squared plus 3x 1 is equal to 0. So let's go ahead and mark what is A, B, C, and D. Let's just go ahead and plug everything into the formula as we usually would with the quadratic. And we get B is this, so we get minus -3 cubed, which indeed just gives us positive 27 over 27, and plus or minus 3 times 3, because that's BC, so that's plus -9 over 6 plus 1 over 2, because minus D over 2A and D is -1. So that makes it a positive, where we get 1 minus, we could divide this by 3, so we get -3 divided by 2 plus 1 over 2, and we get 1 minus 1, which is equal to 0. So with that in mind, we see that everything in the blue is going to be equal to 0. So let's just box the blue up so we know what we're indicating first. And now to indicate the red, we will look at C over 3A, which is positive 3 over 3 because a is 1, and minus b, which is negative 3 squared. We get 9 over 9, which is equal to 0 because that is 1 minus 1. So everything in red is going to equal 0. Let's just box that up again. And let's go ahead and use the formula now, since we're going to have nothing but it's going to look like this. X is equal to the cube root of 0 plus or minus the square root of 0 minus negative 3 over 3a, where a is 1, so we just ignore a, or 1. So we get 3 minus 3, so we end up getting plus 1. So we get x is equal to 1. And in this example, we see that x is equal to 1, and it is only 1, because if we were to use the roots of unity on this, we were multiplying everything by 0, so we would end up getting the solution is 1, comma, 1, comma, 1. So we have a solution of x is equal to 1, but a multiplicity of 3. So that's it for this video, and I hope you guys liked it.